right. First law of thermo. Yeah, energy. Yeah, conservation of energy, right? And the whole energy can't be created nor destroyed. Whole idea here, right? Yeah, energy is conserved, right? So you can't make new energy, not lose new energy, just changing forms, right? Okay, so heat flows. Heat is flowing, energy is flowing from one thing to another. What's the difference between STP and standard conditions? You could say standard temperature is degree C as well. They have a different. What is considered room temperature? Yeah, those are standard conditions. 25 degrees C, right? Standard temperature is what? 0 degrees C. What's standard pressure? 1 atm. Okay. Hey, guess what? So our standard conditions are 1 atm. There's one other thing there that's not included in standard temperature and pressure that is included during standard conditions. It has to deal with a solution and its concentration. 1 molar. Yes. Yeah, 1 molar for standard conditions. Okay. Very good. All right. So let's get to entropy for today. So when we're looking at a spontaneous process is anything that's going to be happening, okay, in the forward direction, essentially. So it's occurring no matter what. It might occur really fast, might occur very slowly, but in any event, it's still happening, right? The kinetics of it are just different. Like if iron's outside, it's going to rust, but it might take a little time for it to rust, okay? But it's still rusting, right? Iron, making iron oxide. So entropy is a measure of disorder. So I relate entropy to, a good way to think about this is I kind of relate entropy to your room at home, right? So you're slowly but surely, things find their way, and your room becomes ordered to very disordered. Okay, it's kind of the natural process of things, right? So if we were to describe that, we would say every time or every item in your room is in the one exact spot it's supposed to be, or the items in your room are in the billions of other spots they could potentially be, right? You go from having clothes hung up in your closet and everything's fine to the point where you can't see the floor anymore and your clothes are just strewn all over the floor by the end of the week, right? Okay, and then you got to put in some energy to get it all cleaned up again so mom gets off your case and whatever else, right? Okay, so the measure of disorder. So if you have, your room is low entropy, you somehow are a neat freak and you're able to keep it clean, okay? Or it might be high entropy and there's just things everywhere and all over the place, right? Sure. Exactly. Or it just means it's all over the place. This is a high disorder. Yeah, it's high entropy. All right. So like when something spills or something, you just be like, nah, entropy. It's not my fault. It's just entropy. Okay. So a couple things in terms of relating them to like states of matter and things like that, right? So a solid, pretty ordered. Liquid, not so ordered anymore, right? Because think of all the different arrangements the liquid molecules could be in. They could be in all sorts of arrangements. Then with a gas, it even becomes even more possible arrangements, right? So more possible for more disorder there. Okay, not only are they moving faster, but there's more space in between the molecules, so they can occupy all those different spaces when they have an opportunity. Okay, and the next two might seem a little counterintuitive, so that's why they're up here. Slow at low pressure. Okay, at low pressure, has greater entropy than high pressure. And it might seem a little counterintuitive, but you need to think about it this way, right? If entropy is disorder and possible arrangements, the number of different possible arrangements you can have with those molecules, think about all the space that's in between the molecules that are not occupied, that they can be order arranged in. So with low pressure, there's more possible arrangements of the gas molecules as compared when it's high pressure and the amount of space between the molecules is much lower, right? So the number of arrangements goes down. It's more like a liquid than it is like a gas at high pressure, right? Because if you think about a liquid, there's not space between the molecules, hardly at all, right? Same thing at very high pressure, okay? Not a whole lot of space between the gas molecules, so the number of arrangements decreases there, okay? Now for entropy of molar masses, you can see that if you have a large molar mass, you have more entropy than if you have a smaller molar mass. Okay, so you can think about how it's got to be the same phase, right? Solid, liquid, or gas got to be the same phase. But you can think about the number of electrons in a larger molar mass substance than something with less molar mass, right? There's a lot more electrons and things in a higher molar mass object, so you start breaking it down to the atomic level and the arrangements of the electrons within those atoms and stuff. So, and we'll talk about this in a second in terms of how, remember heats of formation and all that stuff? Like if you did the packet over the weekend, there's some heats of formation, and elements always have a standard heat of formation of 0, right? Okay, elements have a standard heat of formation of 0, but that is not the case for entropy of elements. Everything, no matter what, has entropy because of the electrons in the atom, because they're moving all the time. So there is some disorder to that element no matter what. Okay? All right, so we keep on moving down. Second law of thermodynamics is talking about spontaneous increase in entropy. So second law is all about entropy and the increasing entropy of the universe. Things are always kind of moving in that direction. The only way it's non-spontaneous is if a little energy goes in. Okay? So the second law of thermodynamics is always one of the arguments against like things like evolution and things like that. But they're actually helping to prove the point, because energy does go in to the system. It's called the sun and stuff. So things like that kind of help the disorder that they're trying to say. Well, the second law of thermodynamics proves that evolution can't happen, blah, blah, blah. So, yeah, but anyway, third law of thermodynamics, this is chemistry, right? So third law of thermodynamics, all it has to deal there with delta G, ultimately. Okay, so, and we'll look at that stuff as we move on here. And I think tomorrow a little bit, we'll do delta G. So delta G is really what's helping us decide whether or not a process is spontaneous or not. It takes into account entropy, enthalpy, right, delta H, and temperature. Okay, all three of those different factors will help us determine whether or not a reaction will be spontaneous or not, based on the way it's written. Okay, and something to keep in mind, like I talked about, delta S for elements is not 0, unlike how it is for H and G. It's not, because the electrons are always kind of moving around. So there is some amount of disorder associated with an element, no matter what. Okay. Also, the beautiful thing about this unit is on the back of your periodic table, you've got all the formulas you need. Okay, just something else. All right, so if we look at a couple examples here of entropy, which substance has higher entropy, solid or gas? Gas, okay. High delta S, low delta S. All right, what about 1 atmosphere and low pressure? delta S, lower S. Okay. All right, if we keep rolling here, start talking about the signs of delta S. Right, so you've got sugar, solid sugars added to water to form a solution. So the sugar goes from being a solid to being dissolved in the water, moving around. Is that an increase or decrease in entropy? Increase, right? So that's a positive delta S. And iodine recondensing to form crystals. So it goes from the gas to a basically solid, right? So becoming more ordered. So it's a negative delta S. So those work. And then the ones that we want to take a look at there with the sign of delta S, when it comes to our reactions, right? Okay, we've got the decomposition of calcium carbonate. So that's a decomposition of a carbonate reaction, just like you've seen before. We heat up a carbonate, we get out carbon dioxide and a metal oxide, so calcium oxide and CO2. So we go from one thing to two things being formed. So not only are we we're breaking something into smaller parts, so more possible arrangements, right? But you're also forming a gas, right? Gases are moving around crazy, right? So that's why this is a positive delta S, more disorder. All right, and the next one there, what we want to take note of here is it's all gases. So comparing states of matter doesn't really matter. But if we look at total moles of gas, well, we got 3 moles of gas on this side. We only have 2 moles over here. So the possible arrangements went down, right? Okay, so we go from more to less stuff. So possible arrangements go down. So that's why that's negative delta S. All right, that one's negative. All right, great. So, and then in looking at and this is really what the part that you need to take in with your periodic table. Right, on the back of your periodic table, you've got this. It's right there. Okay, you've got the formulas, right, for all this stuff, for the standard laws there. Okay, we've got the formulas there for all the thermochem you're going to need. Okay, and a couple electrochem things down there. All right, we've got them. They're on our periodic table, right? So, and also this was asked, like, you don't get a yellow periodic table when you take the AP test, right? It's not yellow like this. It's just in your book. You can rip it out. But it looks just like this, okay? All right. Sorry. So, all right, so let's go ahead and plug this into our equation, right? Products minus reactants for these ones. Products minus reactants. So we got delta S is equal to products. So we got 2 times 248 plus 2 times 38 minus the reactants, which is going to be 2 times 53 plus 3 times 205. I got 572 minus 721. I got negative 149. And something to keep in mind here that is going to be important to us here as we move forward is that's in joules. That's in joules. Okay? A lot of times when we're talking about delta H or delta G, these guys are typically kilojoules per mole. Okay, they're typically going to be kilojoules, so you got to be careful in terms of the unit here. Okay, kilojoules per mole. And notice it's associated with the temperature, so that's going to be important to us as well when we move forward with delta G. Okay, we're going to want to make sure we have our temperature in degrees K, right, and not degrees Celsius. That's another. We have to always make sure our units are matching up, right? Okay, so that's going to be significant for us as you kind of move forward from that. Okay, questions about that? Okay, great. All right, so for that.